Good day, everyone, and welcome to our Summer Tech Talks, brought to you by Scylla University. I am Glauber Costa, VP of Field Engineering here at ScyllaDB. Before we get started, I would like to review a couple of items. First of all, we welcome your questions during today's webinar. Please use the Q&A button located at the bottom of the viewing screen to ask any of the questions you have at any time during the broadcast. We will answer your questions at the end of the presentation. Also, today's webinar is being recorded. A link to the recording and the slides will be sent out via email following the event. Today, one of the key members of my team, Juliana Oliveira, will tell you more about best practices for data modeling in Scylla. I hope you enjoy your session. And with that, I will hand it over to Juliana.
Okay, so hello everyone. This is the best practice for data modeling webinar. We'll talk everything around data, where it starts, where to access it, and how it gets deleted. We'll cover many Scylla-based concepts and go over important points to keep in mind when you're modeling your database. This will be split in three parts. The first part is to understand how data works in Scylla. The second, how storage works and how data is compacted. And the third one, we'll talk about large partitions and how to find them. Don't forget to write your questions and go over them in the end. So, my name is Juliana. I'm a field engineer at Scylla, and I work mostly solving client problems and finding ways to make their databases even more performant. A little about ScyllaDB. We are behind Scylla, the real-time big data database. Scylla is a drop-in replacement for Cassandra, but with 10 times the performance and low tail latency. We are available on the cloud and on-prem with both open source and enterprise editions. So if you haven't already, I encourage you to try Scylla. So for the first part, we will understand how data works in Scylla. In order to understand how we'll model data, we need to understand how data works. So this is important because once we have the right conceptual model of how our data is stored and distributed, what follows gets natural. In this first section, we'll understand where data is and how it's sorted in Scylla in order to be queried later. So why am I seeing this? So SQL data modeling cannot be perfectly applied to Scylla. For SQL modeling, we want relationships and to avoid data duplication. Building queries just later on. In SQL, we want to build a data set according to the query you want to execute. We also want to minimize the number of partitions accessed in a read query, focus on data being evenly spread across the clusters so that every node holds roughly the same amount of data. And also, since Scylla determines where data is stored based on hashing the partition key, choosing a good partition key is crucial. We'll talk about this in a minute. So for our example today, imagine that we work for a pet clinic and we created a table called heart rate. This table has a pet chip ID column, a time column, a heart rate column, and we set the primary key to pet chip ID. So the table is responsible for holding heart rate data for our pet patients, and imagine that we get a new reading every 5 seconds. In this case, since pet chip ID is our primary key, our unique identifier for role in SQL, in SQL is the unique identifier for a partition. But what is a partition? A partition, as you can see in this picture, is a subset of the data that stores on a node, replicated across nodes, and is identified by a partition key. In this case, since we have only one column in the primary key field, Scylla will understand that the partition key is pet chip ID. And just like SQL, since we are reading every 5 seconds, and the primary key must be unique, every 5 seconds we are updating our data. This certainly is not the ideal solution for a pet clinic. Now that we figure out we are losing data, maybe adding a new second column to the primary key must be smart. So we add time to the primary key field, but again, since we're talking SQL, in the primary key won't get completely hashed into the unique identifier. By adding a time column, Scylla will then split the primary key field in two parts. The first part, the pet chip ID, will be a partition key, as we saw before, the partition identifier, and the clustering key is the second part. Uh, and it is different for a partition key because a clustering key is not used to identify a partition. What a clustering key does is sort each row, that is, each container of data, physically inside the partition. It will append into the partition identified by the partition key. Uh, so because the clustering key doesn't get hashed, the behavior is different. First, when we write a query, we may not include the clustering key. Second, we can, for example, run equalities and inequalities in the clustering keys. So these two queries would work in this case because for the clustering key time, we can set time equals to 100 or time is larger than 100. However, if you have two clustering keys, which is this case that I'm trying to illustrate with adding heart rate to the primary key, the sort inside the partition will happen in the same order as the clustering key order. So data will be sorted first using time, and then sorted second using heart rate. We cannot, for example, write a query specifying heart rate and not time because data is physically stored uh, by the clustering key order. So this query here will fail because we're not specifying time, we are only specifying heart rate. But now going back to our original example, looking into our table, knowing how a clustering key works and knowing that we are reading a heart rate every 5 seconds, it's easy to imagine a partition growing large. We are storing data inside one of our partitions using the time column. Since pets can stay under monitoring for weeks, we can have thousands of rows in the same partition, and having partition this big may eventually lead to performance problems, especially if you don't know this is happening. Okay, but what happens to my partition key and where did it go? So as we mentioned, Scylla uses only the first part of the primary key as a partition key. The rest are clustering keys. The partition key, which is patch ID, will get hashed by our hash function. We use murmur3, the same as Cassandra, that generates 64-bit hashes, and then we assign a partition key range for each node that will be responsible for storing keys. In this example, we have a 3-node cluster splitting a token range from 0 to 1200. If we use a replication factor of 2, what will happen is each node holds 2 ranges. In reality, though, Scylla split data in V nodes, which means that we split data in even more ranges. And having V nodes improves especially Scylla cluster rebuilding and streaming times. So to conclude, our partition key patch ID will reside in one of those V node ranges. Scylla knows where it is because of the hashing function, which will always be a value inside the full range. For our second part, we have storage. This part is to understand how data changes on disk and how our queries will affect it. So first, when we read data, we need to be performant. At the same time, we cannot hold everything in memory. Eventually, we need to flush data into disk. When this happens, SStable file is created. SStable is a persistent file format used by Scylla. They are saved as a persistent, ordered, and immutable set of files on disk. And immutable in this case means that SStables are never modified. They are created by a memtable flush, and they are deleted at compaction. More of this in a minute. In practical terms, imagine that we flush data into SStable 1, containing variable a equals to 1. So over time, more data is flushed to other SStables, and imagine that eventually we deleted A, and later memtable flushed this information to SStable 3. Knowing that SStable is immutable, what happens to A? We cannot delete A from all SStables, so in this case, A will be eventually deleted in the next compaction. So a compaction is an operation in which a group of SStables is read to write a new SStable containing only live data. This is efficient because SS tables are ordered, so we read only once. And when data is compacted to SS table 1 plus 2 plus 3, all variables are checked for its most updated value. So for example, since the most updated value for A is delete, A gets deleted on the resulting SS table 1 plus 2 plus 3 compaction. This is why when we delete data from our table, we won't see it reflecting on disk space until the next compaction. There are some different ways to run compactions, and we will list the main ones here. So by default, Scylla uses size-tier compaction strategy, which is very efficient. It compacts SS tables into similar size buckets, so all SS tables have around the same size. But the downside is, uh, since we need to read before writing a new SS table, if it is too big, it can take a lot of disk space. Time window uses size-tier compaction as well, but in time window buckets. Level compaction strategy doesn't require half of this space to be available, but it multiplies write operations by having multiple levels. The size-tier compaction strategy is the default used by Scylla, and is triggered when the system has enough SS tables with similar sizes. As we can see in this graph, it has disk usage spikes, and they happen when we compact all SS tables. For example, when we believe that records are taking too much space and we want to get rid of them by running node2compact all SS tables. So the input SS tables cannot be deleted until we finish writing the output SS table. Right before the end of the compaction, we have the data on the disk twice, in the input SS tables and the output SS tables. We temporarily need the disk space to be twice larger than the data available in the database. So for this compaction strategy to work, we need the disk to be half available all time. In this strategy, leveled compaction strategy, limited size SS tables are divided in levels. Each compaction generates a small SS table which goes to the next level eventually. Since each small SS table doesn't have overlapping key ranges, they can be done in parallel. And also, since they are small, we never have to write a huge SS table as before, which means we don't have the space problem. The downside of the strategy is, since we need to rewrite the same data every time an SS table changes levels, it can be I/O intensive. So let's look to a comparison chart for different compaction strategies to understand when each one of them is used. Here you can see that each has its advantages. Size-tier leveled work for write-only workloads, but one will take twice the disk space and the other will take twice write operations. Level works best for overwrite data since we won't keep all data as long as size-tiered. For many updates, level might be a problem since it also requires many writes. So there are many things to consider. If you are in doubt which is the best strategy for you, you should check our docs in this topic. The link is below. For the third part, we talk about our partitions, what they are, where they hide, and how to find them. So as we saw when talking about clustering keys, we can have a huge number of values under a clustering key in the same partition, leading to a monstrous numbers of rows in your partition. Such partition is called a load partition, and this is a problem when you have a monstrous number of rows, because when you read it, Scylla will try to allocate this in memory, possibly leading to out-of-memory problems, among others. This can get worse if you have a large partition problem combined with a hot partition problem, which is when one of your partitions is particularly more accessed than the others. This hot partition problem usually happens when data is badly distributed. For example, in my pet clinic, I have one particular pet that is always sick, so we generate and read asymmetrically more data for this pet. But anyways, we have ways to avoid this kind of situation and identify the situation. So how to avoid it? First, It's very important to know your data and how it behaves. Second, it's common to increase granularity by adding more columns to the partition key. In this example, we have our heart rate table, and we added dates to the primary key. So our partition is actually not only by patch IDs, but also by days. This makes partitions smaller and easier to manage. In order to track large partitions, we keep a system table called system large partitions. Every time a large partition is written to disk, which means after it's flushed out of main table, we add an entry to this table. It's possible to check how many large partitions are generated over time in order to understand how your data behaves and improve on data distribution if needed. Note that this information will be only available after the data is written to disk, not before. And how do we configure this? Well, the large partition detection threshold can be set in Scylla YAML file with the compaction large partition warning threshold parameter, which defaults to 100 megabytes. So you can use whatever you find relevant for your use case. And each partition bigger than this threshold is going to be reported in the large partitions table and generate a warning in the log. So you can also set up alarms on your logging systems. Well, that's it for large partition. Let's see what we learned today. So we learned why data modeling for SQL is different, and what are partition keys and clustering keys, how partition works, how my data gets stored, and how to find large partitions. If you have any questions, please post them for us to answer. And if you want to dive more into data modeling, you can check our docs in Scylla University. We also have summer talks coming up, so if you're interested, please sign up and join us at Scylla Summit in November. So let's go for questions. Let's see if we have questions here. Okay, so let me hear this one. So this question is, what are the effects of a bad data model? The effects of a bad data model is performance issues. So sometimes when you have a bad data model, you're not seeing the performance that you were promised in the beginning. Is usually because you have a hard partition problem or you have too many large partitions. So Scylla cannot allocate those partitions as well as it should, or those partitions are being accessed in a asymmetrically way in comparison to the other partitions. So performance is the main issue. Um, Another one is, what is the partition limit in ScyllaDB? Well, I don't think we have a partition limit, to be honest. I'll have to check this one out. But we have, okay, so Glauber would like to answer this one, if Glauber is here. Glauber, oh, okay.
So as Juliana said, there are no limits really on the size of the partitions, except when they become too big. You might have those kind of issues, for instance, as Juliana described with large partitions. If your query is reading the entire partition, then obviously this query will take a lot longer, but that doesn't imply that there is a hard limit. A much bigger problem is an inequality in size between some partitions and others, in which case, again, some queries will be much slower and some will be faster. Some nodes will work harder than others, and this might mean that your cluster is not operating at peak capacity. But other than that, there are good rules of thumb of keeping things below a gigabyte, but that's not really a hard limit.
Okay, I hope this answers your questions. Another one is, why can I use inequalities with partition keys? Well, you cannot use inequalities because partition keys get hashed, so you cannot work on those. And I think that's it. Um, Thank you for your question, guys. Uh, I hope you join us in our next Summer Tech Talk, and thank you very much.